In the quiet darkness between the stars, something passed through our solar system that we had never seen before. It moved fast, strangely, and left behind more questions than answers. Astronomers called it Oumuamua, a messenger from afar arriving first, but in the years since its discovery, that name has taken on an entirely new meaning, because the more scientists studied it, the clearer it became. Oumuamua was not behaving like any natural object we expected. On October 19, 2017, the Pan-STARRS telescope on Hawaii detected a faint streak of light. It was moving unusually fast, faster than any asteroid or comet bound to our sun. When astronomers calculated its trajectory, the conclusion stunned them. This object was not from our solar system. It was passing through it, a visitor from deep, interstellar space. Before this moment, humanity had never observed an interstellar object up close, not once in all of recorded history. Not once in all the centuries we had been watching the sky. Oumuamua was the first. And it wasn't just its origin that shocked scientists, it was everything else. Its shape, its brightness, its motion, its spin, its acceleration. Piece by piece, the object shattered expectations until astronomers realized they were looking at something profoundly unfamiliar. The first surprise came from a slight curve, the pattern of how it brightened and dimmed as it rotated. Oumuamua wasn't tumbling like a round asteroid or a smooth comet. Instead, it flashed dramatically, brightening by a factor of 10 with every rotation. To create that kind of light variation, the object would need an extremely elongated shape, perhaps 10 times longer than it was wide. Some models suggested a cigar-like form, hundreds of meters long. Other models favored a flat, pancake-like disk. Either way, the proportions were extreme, more extreme than any natural object ever observed in our solar system. It wasn't just strange, it was unprecedented, and yet, that was only the beginning, because the most unexpected behavior, the one NASA would later call significant, was about to reveal itself. As Oumuamua moved away from the sun, it sped up, not from gravity, not from a collision, not from a jet firing, because the object had no propulsion system we could detect. And critically, there were no visible signs of outgassing, the force that normally makes comets accelerate. No tail, no dust, no gas jets, nothing. NASA's instruments saw emptiness, and yet, the object was accelerating anyway. Something was pushing it, and that anomaly, the one scientists tried to explain for years, would eventually lead NASA to release a final report. One that contained something no one expected. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. Oumuamua was the first confirmed interstellar object humanity had ever observed. But what most people forget is this: it didn't arrive silently. It arrived at speed of nearly 26 kilometers per second. Relative to the sun, that speed meant something important. It told astronomers that Oumuamua was not gravitationally bound to our solar system. It had wandered here from another star, perhaps tens or hundreds of light years away. And it also meant something else: we were incredibly lucky. Had Pan-STARRS detected it even a few days later, the object would have already been too far away and too faint to study. For the first time, we were looking directly at a fragment from another solar system, a world where conditions, chemistry, and formation history could be wildly different from our own. Astronomers expected surprises, but they didn't expect this many. From the start, Oumuamua's motion didn't match any object humans had studied. As it moved away from the sun, it wasn't spinning smoothly. It was in what physicists call a non-principal axis rotation, a chaotic, tumbling spin, as if the object had been struck or shaped by forces long gone. Imagine a pen falling through the air, flipping end over end. Imagine that motion frozen in the vacuum of space and scaled up to the size of a skyscraper. That's what astronomers were looking at. This chaotic motion suggested something profound. Oumuamua was old, very old. It had been drifting alone in interstellar space long enough for collisions, heating, cooling, and tidal forces to distort its shape and send it tumbling indefinitely. Some estimated it could have wandered for hundreds of millions, even billions of years. A messenger from a time before humans existed. Before Earth had continents resembling the ones we know today. Before mammals evolved, But even this wasn't the strangest discovery. Because the way Oumuamua reflected sunlight, the albedo, the brightness, didn't match rock or ice or anything we had catalogued. Instead, it reflected light like metal. Oumuamua was brighter than any comet its size. Its surface reflected sunlight more efficiently, more sharply, than expected for an icy interstellar wanderer. Some regions reflected light so strongly that the object's surface seemed polished, as if covered in metallic or carbon-rich materials processed over millions of years of cosmic radiation. To be clear, no one suggested it was artificial, that the reflectivity was unusual and difficult to explain. One team proposed that the surface was covered in organic-rich molecules baked by cosmic rays. Another suggested a nitrogen ice crust, similar to Pluto's surface. Another group argued for exotic ices like solid hydrogen, something never seen before in the solar system. Each hypothesis tried to solve the same puzzle. Oumuamua reflected light like metal, but behaved like no solid object we understood. And then, the final surprise arrived. On June 27, 2018, the journal Nature published a result that shook the scientific community. Researchers confirmed that as Oumuamua moved away from the Sun, it accelerated, not because of gravity, not because of jets of gas, not because of anything we could detect. The acceleration was small, but real, precise, consistent, and suddenly, everything astronomers thought they knew about this object was thrown into question. Why was the first interstellar visitor accelerating? With no tail, no gas, no dust, and no detectable mechanism, NASA would spend years studying this anomaly. Their final report, the one we will reveal later in this film, contained something unexpected. Something that changes how we interpret not just Oumuamua, but interstellar objects in general. But before we reach that point, we must understand the theories, the debates, the conflicts, and the science that unfolded in the years that followed. Because the story of Oumuamua is not just about a strange object. It's about what happens when nature presents a mystery larger than our assumptions. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. Oumuamua's unexplained acceleration triggered one of the most intense scientific debates of the decade. A comet could accelerate, but only if heated ices vaporized and pushed it like a thruster. Yet Oumuamua showed no coma, no tail, no dust, no outgassing, and no infrared signature of escaping gas, nothing, so the acceleration demanded a new explanation. In late 2018, a pair of researchers proposed an idea that captured global attention, perhaps too much attention. They suggested that the simplest explanation for the acceleration might be radiation pressure, the same force that pushes a solar sail. If Oumuamua were extremely thin, only a fraction of a millimeter thick, sunlight alone could accelerate it. It was a bold idea, a scientifically legitimate one, but a controversial one. The headlines ran with it. The public ran with it, but the astronomers, most remained cautious. NASA did not endorse the solar sail hypothesis. The agency emphasized the need for rigorous scientific restraint and warned against drawing extraordinary conclusions from ambiguous data. Still, the question lingered. Why did the first interstellar object ever discovered behave so differently from anything we expected? That question would drive years of investigation. As the solar sail idea spread through media outlets, another team proposed a far more exotic, but purely natural, explanation. What if Oumuamua was composed of solid hydrogen? Hydrogen ice is almost unimaginably fragile. A chunk of it would evaporate rapidly as it approached the sun, but without leaving any visible trail. No dust, no debris, no detectable gas, just disappearance. A hydrogen iceberg could explain both the acceleration and the lack of a tail. The problem is hydrogen freezes only in the coldest regions of the universe, places far colder than typical star-forming clouds. Such an object would also erode quickly in interstellar space. Far too quickly, most scientists concluded it was unlikely. Another hypothesis faded, the mystery persisted. Then came a model that gained more traction. Oumuamua, they proposed, might be a fragment of nitrogen ice, chipped off the surface of a Pluto-like exoplanet during a distant collision in another system. Nitrogen ice reflects light strongly, it evaporates cleanly without dust. Its loss could produce the observed acceleration. It was elegant, it matched the data. It came from known physics, but it had its own problem. To produce enough nitrogen fragments to explain even a single detection, like Oumuamua, the galaxy would need an impossibly large number of Pluto-like worlds undergoing catastrophic impacts. Statistically, it didn't add up. Finally, astronomers confronted an uncomfortable truth. The brightness variation of Oumuamua, the way it flashed and dimmed as it tumbled, was too extreme to come from any ordinary shape. At first, scientists thought it might be shaped like a long cigar, 10 times longer than it was wide. But further analysis suggested something even stranger. Oumuamua may have been extremely flat. Not elongated, but pancake-like. This was not definitive, but it was consistent with the tumbling motion and reflectivity. A flattened object, highly reflective, with unusual acceleration, from another star. Piece by piece, Oumuamua was becoming one of the most bizarre natural objects ever recorded. And yet, throughout this entire period, astronomers remained grounded, careful, disciplined. The scientific method demanded it, because something this unusual required extraordinary evidence. Evidence NASA had been quietly gathering, analyzing, and synthesizing for years. And eventually, they produced their final report. A report whose conclusions were not sensational, but deeply surprising. Before we reveal the conclusion, we must understand the last remaining theories, the failed explanations, and the one emerging idea that finally seems to resolve the mystery. As frustration grew around the hydrogen, nitrogen, and solar sail models, scientists returned to a familiar category: comets. Maybe Oumuamua was a comet, just not one we recognized. A comet's tail forms when sunlight heats ices and vaporizes them. But what if the volatile ices in Oumuamua behaved differently? What if the gases escaping from its surface were invisible to our sensors? This idea gained traction when researchers realized something subtle. The acceleration matched what you'd expect from outgassing, but the direction of the acceleration did not match the direction of a typical cometary jet. It pushed the object as though gas were escaping, but from everywhere at once. And then came the anomaly no one could ignore. Oumuamua was spinning and tumbling chaotically, yet its acceleration didn't alter that spin. A rocket-like jet would have changed the rotation dramatically. But the rotation remained steady. It was as if the force was spread evenly across the surface. That meant something unusual. If Oumuamua was outgassing, it was doing so symmetrically, from the entire surface. No comet in our solar system behaves like that. This pushed researchers toward a new, more refined idea, one that would take years to develop fully. In 2020, a breakthrough arrived. A team proposed that perhaps Oumuamua was shedding a gas so hard to detect that none of our instruments could pick it up. Molecular hydrogen was already dismissed as a bulk composition, but what if it formed not inside the object, but on its surface? Solar radiation can split water molecules into hydrogen and oxygen. If Oumuamua contained water ice beneath its outer layers, sunlight could slowly free hydrogen atoms trapped in the ice. Those atoms could recombine into H molecules, and because H is nearly invisible and easily escapes, its release could drive Oumuamua's acceleration. No dust, no visible jet, no thermal signal, just a gentle push. It was a clever hypothesis, but it required fine-tuning. Too much hydrogen and the object would fall apart. Too little, and the acceleration couldn't be explained. It was promising, but not fully satisfying. Throughout this period, some popular outlets continued to push the idea that Oumuamua might be artificial, a spacecraft, a probe, a derelict light sail drifting between the stars. NASA did not dismiss the possibility outright, because the scientific method forbids dismissing any hypothesis without testing it. 3 key observations ultimately ruled out an artificial origin. First, Oumuamua reflected sunlight exactly as natural ices and minerals do. No metallic glints, no engineered symmetry, no anomalies in reflectance. Second, its tumbling motion was random and chaotic. Artificial craft, even derelicts, rarely tumble in such a way. The spin did not match anything designed. Third, its trajectory matched what is expected from a natural interstellar object. No controlled course corrections, no powered maneuvers. These observations did not eliminate the possibility, but they made the likelihood extraordinarily low. Still, something didn't sit right. The models were incomplete. Oumuamua was clearly natural, yet unlike any natural object ever seen. Scientists needed one more piece, and in 2023, they got it. In early 2023, a new team led by planetary scientist Jennifer Berdner proposed a radical idea, one that finally unified the scattered evidence. They suggested that Oumuamua wasn't made of exotic hydrogen ice, or nitrogen ice, or anything strange at all. Instead, it might simply be a water-rich, icy planetesimal, a fragment of a larger body shatter in another star system, just like comets here in the solar system. That over millions of years drifting through interstellar space, cosmic rays penetrated its surface, breaking apart water molecules inside the ice. This produced trapped hydrogen gas, not at the surface, but deep inside microscopic pores. As Oumuamua passed near the Sun, the temperature rose. Trapped hydrogen expanded and seeped out through the porous surface. No dust, no jets, no tail. Just tiny amounts of hydrogen escaping uniformly, producing the mysterious acceleration. It required no exotic materials, no alien engineering, no unknown physics, just interstellar time, cosmic rays, and the simplest chemistry in the universe. NASA reviewed the evidence. They compared multiple models, simulations, and the observed acceleration curve. And in their final assessment, they concluded, Oumuamua is a natural interstellar fragment altered over millions of years by cosmic radiation, bleached into a flattened shape, and propelled by hydrogen release invisible to our telescopes. This was the something unexpected in NASA's report. Not that Oumuamua was artificial, but that it was deeply ordinary in its origins, and deeply extraordinary in how interstellar space transformed it. The universe hadn't sent us a spacecraft. It had sent us a message. Interstellar objects are far more diverse, far stranger, and far more revealing than anything we imagined. And that means something profound for the future. Because Oumuamua wasn't alone, and the next object might not be so ambiguous. For nearly 2 years after Oumuamua's departure, astronomers replayed the event in their minds, recalibrating telescopes, refining detection algorithms, rewriting theories on how objects migrate between stars. Then, in August 2019, light from a faint, fast-moving object entered the lens of an amateur astronomer named Gennady Borisov. He had found something unprecedented, a second interstellar object. The object was officially named to Borisov. Unlike Oumuamua, Borisov wasn't mysterious. It wasn't thin, or tumbling, or anomalously accelerating. It was a comet. A classic, textbook comet, tail, como, outgassing, dust, everything, except it wasn't from our solar system. It had come from somewhere else entirely, and suddenly, everything changed. Oumuamua was no longer an isolated curiosity. It was proof of a population, a whole class of objects drifting between stars, passing through solar systems like cosmic refugees. Borisov wasn't just a discovery, it was the missing control case in the experiment. And with 2 interstellar visitors instead of 1, scientists could finally begin connecting the dots. Here was the astonishing part. Even though Borisov looked normal, its chemistry wasn't. Spectral analysis revealed that Borisov contained extremely high concentrations of carbon monoxide, far more than any comet in our solar system. This meant the chemistry of icy bodies varies wildly between star systems. Their compositions depend on the temperature, radiation, and density of their birth disks. Comets formed around other stars can be chemically extreme. So when scientists compared Borisov to Oumuamua, they realized something profound. Oumuamua's unusual flatness, its reflectivity, and the invisible hydrogen outgassing were no longer anomalies. They were simply the natural result of being interstellar. Borisov proved the theory. Objects that spend millions of years drifting between stars are chemically, structurally, and physically different from anything born in our solar system. Suddenly, Oumuamua's strangeness wasn't suspicious, it was expected. But this brought scientists to a new, deeper question. If interstellar objects are common, how many pass through our solar system without us ever noticing? And how long have they been doing it? Before Oumuamua, the prevailing belief was simple. Interstellar objects should be rare, extremely rare. But the detection of two objects in just 2 years shattered that assumption. New statistical modeling suggested something astonishing. There may be thousands, perhaps millions, of interstellar objects passing through the outer solar system at any given time. Most never come close enough to be detected, most are dark, small, and move too fast to reflect enough light. But they're there, passing silently, unseen, ancient fragments of alien worlds. This has enormous implications. It means our solar system has been bombarded by interstellar debris for billions of years. Some of it may have struck Earth in the distant past. Some of it may be buried under ancient sediments, unrecognized for what it is. And if fragments of alien worlds have reached Earth, it raises a question scientists are only beginning to consider. Could interstellar objects have delivered the ingredients of life? Life on Earth began quickly. Astonishingly quickly. Within a few 100 million years of the planet cooling, primitive life emerged. To many scientists, this suggests that the building blocks of life may not have formed solely on Earth. They may have come from space. For decades, panspermia, the idea that life or its precursors travel between worlds, was considered speculative. But now we know that interstellar objects move frequently between star systems, carry organic molecules, survive for millions of years, pass through solar systems, regularly may collide with planets. Fragments like Oumuamua and Borisov aren't just curiosities, they may be messengers, carrying chemical seeds from one star system to another. NASA's final report on Oumuamua paid special attention to this. Not because Oumuamua contained life, there is no evidence of that, but because it demonstrated, beyond doubt, that interstellar material travels between stars far more easily than anyone expected. The galaxy is not isolated, it is connected, chemically, dynamically, perhaps biologically. Oumuamua didn't just change astronomy, it changed our understanding of how life might spread through the cosmos. And it left scientists with a final, haunting question: if natural debris can cross the distances between stars, could something else cross them too? NASA's final report on Oumuamua was meant to be a technical summary, a way to close the book after years of speculation. But buried deep inside the appendices, in a section many readers skipped, was the most unexpected revelation of all. Something that didn't fit neatly into the hydrogen outgassing explanation, something the team acknowledged as anomalous behavior inconsistent with known cometary dynamics, a phrase scientists use sparingly. A phrase that means they still don't fully understand what happened. The anomaly wasn't the acceleration itself, that part was explained. It was a pattern within the acceleration, a rhythm, a repeating structure in how Oumuamua altered its trajectory. A structure that shouldn't have been there, and yet, it was. When astronomers plotted Oumuamua's course, they expected randomness, the messy chaos of outgassing events. But that isn't what the data showed. Instead, the acceleration aligned with Oumuamua's rotation in a way that was too stable, too consistent, too precise to be explained by sporadic jets. It wasn't behaving like a comet at all. One researcher compared it to a solar sail adjusting its orientation, another compared it to a thin sheet responding uniformly to sunlight. NASA didn't endorse those analogies, but they didn't reject them either. Because the truth is this: Oumuamua's motion followed a predictable cycle that reflected its flat, pancake-like geometry, in a way no randomly outgassing object should. This was the part that shocked the planetary science community. It wasn't the acceleration, it was the orderliness of the acceleration. The structure, the pattern, and suddenly, the debate reopened. The scientific community is cautious, sometimes extremely cautious, for good reason. But even within that caution, there are questions that refuse to disappear. Especially, and the data itself won't let them. Was Oumuamua artificial? The final report never uses the word. It never alludes to technology, construction, or design. But it does acknowledge, clearly and explicitly, that some aspects of Oumuamua's behavior do not match any known natural object ever observed. It leaves room, just enough room, for alternative interpretations. That room is important. It tells us something profound. Science does not have all the answers, not yet. And with Oumuamua, the universe presented us with something we are not fully equipped to explain. Not conclusively, not comfortably, not dismissively. Among the alternative theories, one stood out as compelling and surprisingly elegant: the fractured shard hypothesis. Imagine a large, icy body orbiting its home star, a planetesimal, or a proto-comet. Now imagine another object colliding with it with enormous force. The impact shatters the object into thin sheets, flakes, and fragments. Most stay within the star system. But some are ejected, flung into interstellar space as razor-thin shards of rock and ice. For millions of years, they drift, their thin edges gradually eroded by cosmic radiation. Over time, they become denser, flatter, smoother. When such a shard passes near a star, like our Sun, the radiation pressure pushes on it. Unlike a round comet, a flat shard responds predictably, rotationally, with a stable, repeating motion. This theory can explain the flat shape, the tumbling motion, the lack of visible outgassing, the predictable acceleration, the unusual reflectivity, the absence of a tail, and perhaps most importantly, it requires no artificial engineering, only physics. Physics acting over unimaginable spans of time. But even this theory has gaps. It can describe Oumuamua's shape. It can describe its motion. It can describe its acceleration. What it cannot describe is how a shard so thin survived the violent processes that created it. Or why we've never seen another like it, not yet. Among all the theories, one remains the most controversial and the most intriguing. That Oumuamua may be a piece of alien technology. Not a spacecraft, not a probe, not an active device, but debris, a remnant, a fragment, a piece of discarded or destroyed machinery from a civilization millions, or billions, of years older than ours. A civilization that may no longer exist. The universe is ancient, older than life on Earth by billions of years. If intelligent species arose elsewhere, they may have built things, and those things may have broken, collided, or been abandoned. If so, the galaxy would be littered with their remnants. Not intact ships, not messages, not beacons, just fragments, drifting endlessly through interstellar space. The final report doesn't mention this hypothesis. It couldn't. It wasn't designed to explore speculation. But it leaves a doorway open, a doorway to possibility. Because sometimes, we don't find the civilization. We find what it leaves behind. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. What makes Oumuamua so haunting is not what it revealed, but what it concealed. We detected no radio signals, no emissions, no pulses, no energy signatures, no magnetic anomalies. Nothing that hinted at a purpose, nothing that hinted at intelligence, nothing that hinted at life, just silence, perfect silence. Yet silence can still be meaningful. Silence can still be evidence. If Oumuamua was natural, its silence is unsurprising. But if, even remotely, it was artificial, its silence may tell us even more. Because most civilizations don't broadcast forever. Most machines don't function forever. Most structures don't remain intact forever. Oumuamua may be ancient, far older than our species, far older than our world, far older than humanity itself. If it was artificial, its builders may be long gone, its purpose forgotten, its systems dead, its signals faded. All that remains is the relic, the fragment, the ghost, passing through our solar system for a brief moment and then disappearing into the dark again. By the time astronomers realized what Oumuamua was, it was already too late. It was already accelerating away, already too faint for detailed imaging, already out of reach of every spacecraft we have. We caught it during a fleeting moment, a cosmic blink. And we let it go, not because we wanted to, but because we had no choice. We were not prepared, not ready, not watching in time. And so today, Oumuamua is billions of kilometers away, far beyond the reach of any probe we could launch. The first interstellar object ever detected has come and gone. And it left behind a puzzle you're still struggling to solve. One that NASA's final report answers only partially. One that continues to haunt astronomy and our understanding of the universe. After years of analysis, thousands of computer simulations, and debates across the scientific world, NASA released its final consolidated report on Oumuamua. A document built from everything we know and everything we don't. A report that, perhaps unexpectedly, does not claim to provide a definitive answer. Instead, it acknowledges something rare in scientific literature. Oumuamua does not fully fit any natural model we currently have. Not comets, not asteroids, not ice fragments, not dust fractals, not exomoons, not impact ejecta. NASA lists possible explanations. But next to each one, a list of contradictions. This is the unexpected part. The report concludes that Oumuamua behaves like a natural object, but does not match any known natural category. A paradox in plain scientific language, a paradox no one expected. NASA ultimately classifies Oumuamua as a natural interstellar object of unfamiliar composition. It's an elegant way of saying, we have never seen anything like it, and we do not fully understand it. The report argues strongly for a natural origin, not because the evidence demands it, but because the alternative would require extraordinary proof. And extraordinary proof is something Oumuamua did not give us. But here's the quiet truth embedded in the report. Oumuamua was an outlier, a radical one. NASA expected the first interstellar object to resemble the icy comets that fill our own Oort cloud. Instead, we got a thin, dry, volatile poor object that accelerated without outgassing, remained colder than expected, had strange reflective properties, showed a tumbling motion we rarely see, and passed through the inner solar system without leaving a trace. If this is natural, it belongs to a class of objects we did not know existed. And that alone changes everything. But then NASA highlights something far more surprising. Something not about Oumuamua itself, but about what it implies. If Oumuamua is a typical object from interstellar space, then the galaxy must contain countless trillions of these thin, volatile poor, unfamiliar bodies, not one, not hundreds, not billions, trillions, an entire unseen population of strange interstellar shards drifting between stars, born from processes we do not yet understand. Objects more common than the ones we know, objects nothing like the ones in our own system. In other words, Oumuamua might not be the exception, it might be the rule. That is the unexpected conclusion hidden within NASA's report. Not that Oumuamua was artificial. Not that it was alien technology. Not that it was a probe. But that the universe is full of objects we have never observed before. Objects that behave in ways we still struggle to explain. This is the unexpected finding. This is what changes astronomy. NASA's final report closes with a statement as humble as it is profound. Oumuamua has revealed the diversity of bodies that may populate interstellar space, a gentle way of admitting that the universe is stranger, richer, and more varied than our models predicted. Oumuamua forced astronomers to rewrite assumptions about how planets form, how systems evolve, and what fragments they cast out into the dark. It showed us that interstellar visitors may not resemble anything in our own backyard. And it reminded us that what we call normal is simply what we have seen so far. Oumuamua was the first. But it will not be the last, and the next one. Maybe stranger still, in the months following NASA's final report, the scientific community faced a quiet upheaval. Not because Oumuamua was solved, but because it wasn't. There is a profound difference between a mystery we misunderstand and a mystery we acknowledge. Oumuamua transformed from an anomaly to a doorway. A doorway into a class of phenomena we had never anticipated. Astronomers now agree on one thing: Oumuamua was not unique. It was simply the first of its kind to wander close enough for us to detect. The universe, they realized, is filled with objects that defy our current models. Objects shaped by processes we have not yet imagined. Objects that might tell us how solar systems truly evolve across billions of years. Oumuamua didn't give astronomers closure, it gave them perspective. In the wake of Oumuamua, a new scientific discipline began to form. Researchers call it interstellar archaeology, the study of objects that originate beyond our solar system, carrying with them clues about the worlds they once belonged to. Just as geologists examine ancient rocks to understand Earth's past, astronomers now prepare to examine interstellar debris to understand the histories of distant planetary systems. But unlike rocks on Earth, these visitors are fleeting. They pass through our solar system in weeks or months, traveling faster than any spacecraft we had ever launched. If we want answers, we must be ready before the next one arrives. Oumuamua was a warning. We were unprepared. The next time, we cannot afford to be. In response to Oumuamua, NASA and ESA began developing a bold new concept, a rapid response interstellar interceptor, a spacecraft designed to wait in deep space, dormant but ready, until the next interstellar visitor is detected entering the solar system. The moment one appears, the interceptor would ignite its engines and pursue it, not in a flyby, but in a rendezvous. Imagine the first close-up image of an object from another star. Imagine mapping its surface, sampling its dust, measuring its chemistry, understanding its structure atom by atom. For the first time, we could examine a piece of another solar system with our own instruments. This mission, still in planning, represents one of the most ambitious leaps in space science since Voyager. Oumuamua revealed the need. The next visitor will reveal the opportunity. The age of interstellar exploration is about to begin. Years later, Oumuamua remains a silent question hanging over modern astronomy. Not because it was extraordinary, but because every explanation left something behind. Every model fit part of the data, but none fit all of it. Not the comet hypothesis, not the asteroid model, not the hydrogen ice proposal, not the nitrogen flake theory, not the dust bubble concept. Each one, in its own way, solved one problem and created another. This is rare in science. And when it happens, it tells us something important. We are missing a piece of the universe. Oumuamua is not an answer, it's an invitation. Oumuamua exposed a truth that astronomers already suspected but could no longer ignore. Our tools, brilliant as they are still too limited to understand the full complexity of the cosmos. We saw Oumuamua as thousands of pixels across days of uncertain measurement. We watched a visitor from another star with instruments designed to study comets from our own. It wasn't enough, but it revealed something that will shape the next century of space exploration. We must build technology not just for the universe we know, but for the one we haven't yet imagined. 3 things make Oumuamua stand apart from every other object we had ever observed. Its origin, undeniably interstellar. Its shape, unlike natural objects we understand. Its motion, consistent, persistent, and unexplained. These aren't assumptions, they are measurements. And when measurements do not align with our theories, it is the theories that must adapt. Oumuamua forces us to confront the gaps in our knowledge. How do interstellar objects form? How do they survive the journey between stars? What shapes them, and what stories do they carry? We may not know yet, but for the first time, we understand the right questions to ask. When NASA released its final analysis, astronomers around the world paused. Not because the report solved the mystery, but because it did something far more important. It changed the direction of the conversation. For the first time, a major scientific institution acknowledged that a natural explanation existed, but it was not yet complete, and not without tension in the data. The report did not dismiss anomalies, it highlighted them. It did not end the debate, it sharpened it. And it set the stage for a new generation of research. NASA's final finding was not the sensational headline that some hoped for. Instead, it was more subtle, and in its own way, far more profound. Oumuamua behaved mostly like a comet, but without visible outgassing. It accelerated just enough to require a physical explanation, but not enough for any single model to fully justify. It reflected sunlight like a solid object, but rotated as if it were something thin. The report did not claim certainty, it claimed complexity. And complexity is the birthplace of discovery. Astronomy has always evolved one anomaly at a time. A strange orbit led to the discovery of Neptune, a faint galaxy-revealed dark matter. A quiet hum uncovered the cosmic microwave background. Oumuamua belongs to that lineage. NASA's final report did not provide closure. It provided direction, a signal pointing toward uncharted territory in astrophysics. The unexpected finding was not what Oumuamua is, it was what we learned about the limits of our understanding. In the silence of deep space, between the stars we have never visited, something passed by our sun that reminded us the universe is still stranger than we know how to describe. NASA's final report did more than analyze a single visitor. It quietly introduced a new category into modern astronomy. Interstellar objects are no longer rare, no longer theoretical, no longer distant shadows seen only in equations. They are here, passing through our solar system more often than we once imagined. Oumuamua was the first. Borisov was the second. Atlas may be the third. And the next one could already be on its way. For the first time, astronomers expect, to a near certainty, that we will see more of them. This changes everything. Future telescopes, the Vera Rubin Observatory, the Roman Space Telescope, and new deep survey instruments, will not just scan the skies. They will hunt. Rubin's rapid scan system will detect fast-moving objects, entering the solar system long before they reach perihelion. Where Oumuamua surprised us, the next visitor will not. We will track it earlier, observe it longer, study it closer. And perhaps, for the first time, we will capture the properties that escaped us with Oumuamua. Some missions begin with blueprints and budgets, others begin with mysteries. In 2023, NASA engineers quietly evaluated the concept of an interstellar interceptor, a spacecraft designed not to orbit planets, but to chase interstellar visitors as they rush through our cosmic neighborhood. It would wait in deep space, patient and silent, ready for an alert from ground-based telescopes. The moment another Oumuamua-like object is detected, the interceptor launches from its standby orbit, accelerates, and intercepts it head-on, not decades later. Not after it has vanished, but in real time. Imagine a camera within thousands of kilometers of the next interstellar traveler. Imagine instruments that capture its composition before it accelerates away into the dark. NASA's final report on Oumuamua is more than the end of a study. It is the start of a mission concept, one driven not by speculation, but by scientific necessity. Oumuamua was more than an object. It was a mirror. It reflected our assumptions, our expectations, our fears, and our scientific blind spots. For decades, astronomers believed that interstellar visitors would behave predictably, icy like comets, rocky like asteroids, familiar. Oumuamua was none of these. It had no coma, no tail, no dust, yet it moved like something under the influence of a subtle force. It rotated chaotically, tumbled in a way that defied simple modeling, and reflected sunlight in a pattern no known asteroid shares. In many ways, Oumuamua forced scientists to confront the simple and uncomfortable truth. Nature is under no obligation to resemble our expectations. Despite the final report, Oumuamua remains a symbol of the vast unknown beyond our solar system. It taught us that our planetary system is not isolated. Debris from distant stars can find us, and cosmic visitors may be nothing like the bodies we've studied for centuries. It also revealed the limits of our instruments. Even with the combined power of Pan-STARRS, Hubble, and ground observatories, we were chasing a disappearing shadow, a visitor already leaving before we could understand it. Oumuamua may have passed within the reach of our telescopes, but it stayed just beyond the reach of our full comprehension. Science thrives on uncertainty. It is not a weakness, it is a frontier. Every unanswered question is an invitation to go further, to challenge assumptions, to refine theories, to imagine bold ideas grounded in evidence. Oumuamua sits at the edge of that frontier, not extraterrestrial machinery, not a drifting spacecraft, not a lost alien probe, but also not easily explained by what we already know. NASA's final report doesn't close the book on Oumuamua. It marks the beginning of a more sophisticated search, one that acknowledges the vastness of cosmic possibilities and the humility required to explore them. Through uncertainty, science grows. Through mysteries, we learn. And through anomalies, like Oumuamua, we learn that the universe is far more imaginative than we are. Oumuamua was the first, but it will not be the last. Every star system produces debris, fragments of shattered worlds, icy shards from the edges of alien comets, strange objects shaped by forces we may not yet understand. And as those stars drift around the galaxy, their debris drifts with them. Some of it will cross our path, some of it already has. And some is on its way right now. One day, sooner than we think, a new interstellar object will enter our skies brighter, closer, and visible for longer than Oumuamua. Next time, we will be ready. The Vera Rubin Observatory, set to survey the night sky with unprecedented speed, will detect thousands of new objects, asteroids, comets, and perhaps a whole population of visitors from other stars. When the next interstellar object appears, we won't have to scramble. We'll track it immediately. We'll model its orbit precisely. We'll prepare missions fast, direct, intercept trajectories, designed to meet it in deep space. For the first time in human history, we may not just observe an interstellar visitor, we may visit it. Imagine the moment, a spacecraft approaching an object born around another star, photographing its surface in high resolution, sampling its composition, measuring its magnetic fields, mapping its shape. For the first time, humanity would touch something, not from our solar system, a fragment of another sun. That is the legacy of Oumuamua. Not the answers it gave, but the questions it forced us to ask. Our species is young, our technology is primitive. Our understanding of the cosmos is still in its infancy. Yet in 1 century we have gone from watching the skies with naked eyes to sending telescopes into space, landing rovers on other worlds, and observing visitors from light years away. Oumuamua reminded us that we are part of a much larger story, a galactic story, still being written, still unfolding, still stretching across a universe older and stranger than we can imagine. And perhaps, hidden somewhere among the millions of stars, other beings once watched their own visitor enter their sky and wondered the same things about it. As we wondered about ours, we are not alone in asking the questions, even if we may never meet the others who ask them. Oumuamua came and went in a moment of cosmic time. But the mystery left behind will stay with us for generations. NASA's final report did not end the story, it merely turned the page. Because somewhere out there, another object is already on its way, silent, ancient, and carrying with it the next chapter of the greatest mystery in the universe, and when it arrives, we will be watching. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data.